of
magnetic field.
Okay. Right. I think from where I stopped. So, okay. So, starting from this, we have magnetic materials, and these are magnetic materials that respond to magnets. Some of them by being magnetized, and some by just being able to be attracted by magnets. So ferromagnetic materials. Now, a ferromagnetic material is one that is strongly attracted to a magnet and can be permanently magnetized. Strongly attracted to a magnet and can be permanently magnetized. They have high permeability. Example, we're talking about iron, cobalt, nickel, and steel. Yes. Okay. We're talking about the fact that they have more concentration of iron containing compound as ferric compound. So ferric compounds are small, they are small iron rich compounds. You understand? So they are rich in those things. Paramagnetic materials, these ones are weakly attracted to magnets. They are magnetized in the direction of the field only. They do not remain magnetized. Examples: aluminum, platinum, and magnesium. You want to keep those examples in mind because they're not ask you in an video exam. Which of the following is paramagnetic? You want to remember magnesium, just remember aluminum. Very, very good. Diamagnetic, weakly repelled. Now, there's a difference between that and this. This one is strongly attracted to a magnet. This one is weakly repelled. Paramagnetic is weakly attracted. So these ones are weakly repelled by magnets, magnetized opposite to the field. So if you want to, like for example, look at this setup here. If I'm trying to magnetize this guy, magnetizing means trying to convert them to a magnet. I'm trying to magnetize this one now that is red here. We make this one on here become the south pole, which will be red. So it is going to give him an opposite polarity distribution to his own. So that's the example of diamagnetic material. You have copper, silver, bismuth, and even water. Together. Anti-ferromagnetic materials. This one's adjacent magnetic moment aligns in opposite direction. Not net magnetization. Example, magnesium, chromium. All right. Thank you very much. Next slide. Magnetic field concept. Magnetic field is the region around a magnet, a current carrying conductor, or a moving charge in which magnetic force can be detected. If I generally I do tell you guys, whenever I get the word a field, just know it's a region of space where a specific type of force can be felt. In this case, I'm talking about the magnetic field, so we'll be feeling the magnetic force. And a magnetic force is all about attraction or repulsion. So the key idea is this: a magnetic field is produced by moving electric charge or permanent magnet. So that's the funniest thing. You don't form a magnet. It's just about a charge moving. Whenever charge moves, magnetic field are generated. Understand? Whenever charge moves from one place to another, magnetic field are generated. Sometimes it's dependent on the speed at which they used to move through. You understand? So it's very important to know that. Another thing is exact magnetic force on moving charge. Current and conductors of magnetic materials. It's a vector field that's both magnitude and direction. Then it stores energy and can do work on suitable bodies described by a few quantities such as magnetic strength, magnetic flux density, which are the differentiating as time goes on. Sources of magnetic field, there are permanent magnets, which are natural ones like lodestone. Electric current, straight conductors. Whenever current of moving in straight conductors, they can produce magnetic forces. And they do that following the right hand rule, which I'm explaining to you today. So we have electric current in coil and solenoid, as well as moving electric charge. Next slide. Magnetic field. The magnetic field is the space around a magnet or a current in which the magnetic pole or a moving charge experiences a force. We've explained that earlier. We've mentioned that we said is a magnetic field at a point is said to exist if a non-equal place at that point experiences a force. Characteristics, zooming on that. One of the characteristics is that their line of force never cross each other. They never intersect. So it is a vector field. It's a vector field. It has directions from north to south outside the magnet, but the reverse within. Inside the reverse within. So it's strength in the uniform or the non-uniform. It can be represented by two. It can be represented by two lines. It based the superposition theory. Okay. So this, yes, I think that magnetic lines do not superimpose themselves and form all those interference that are really destructive or constructive. They can only the field of different magnets can overlap, but the field from the same magnet cannot overlap.
Like,
Even there's even like of the same magnets. It can never overlap. So yeah, this is how the bar magnets magnetic field distribute itself on the magnets. But on the current carrying conductor, it forms a hole. Now everybody, please grab a pen. Grab a pen to your right hand. Hold your right hand around your pen. Just hold your right hand like this around the pen. Then free your tongue upward. You see the direction of your tongue. It tells you the direction of the magnetic field. If this your pen was a wire, field electron. So when you do that, you see, if I do that now, this is you see, it means, look at this, it means these are all that four fingers showing the direction of the magnetic field produced by the movement of current in this direction. So you'll be hearing also the word out of the page into the page. So if I do my like this, it means my hand is coming out of the page from the right and entering back into the page. And the other hand, do you know what I'm saying? So just in case you don't use the word out of the page, out of the page is like the field is coming out from this side.
where is the out?
Z axis. Yes. So in the solenoid also, to look at that, the solenoid next, magnetic field strength, which we call H. Let me zoom on it a bit. So magnetic field strength quantifies the intensity of the magnetic field at a point produced by a current or magnet. It's the force experienced by unit pole. Yeah. So you can see H here equals to F by where F is magnetic force on a pole, M is the pole strength, and H is magnetic field strength. Very important to know that. Field due to simple sources, long straight conductors. You see here H is equals to I multiplied by R. Therefore, it's solenoid inside a different one. Okay. Magnetic flux. Just as we did electrical flux the other time when we associated on Gaussian surfaces, we were able to also discuss the flux in the magnet. So we hear about magnetic flux, we're talking about the total number of magnetic fields passing through a surface. And we know that when the number of magnetic field lines are much, it simply signifies that what? There is high intensity of magnetic field around that region. Do you understand? Do you understand what I'm saying? So, the definition, magnetic flux through a surface is the total number of magnetic field lines. So when we get to magnetic field and flux density, that's what we're talking about, how those lines come close to themselves, something like this. If this was a magnet, right? Imagine this was a magnet. You see the way I brought all these lines closer to themselves? It signifies that these regions here, we have a high magnetic flux density. But we are just talking about how many lines are there. 1, 2, 3, 4, 5. That one is talking about magnetic flux. The amount of magnetic field lines coming out, acting over a surface. Okay, the total number of lines represent our magnetic flux. Yes. So that's mathematical expression. We now know that the magnetic flux will be equal to the magnetic field multiplied by area. But it doesn't end here. We put cos theta. Yes. So, theta represents the angle between the magnetic field and the normal line. It represents the distance, the angular distance between what? Let's imagine this is the surface. This is the normal. And if this is the magnetic field, this angle between the magnetic field and the normal line is what we call theta. Very good. So angle between B and the normal, so this is what we call theta. So first thing first, flux. Flux is a scalar quantity. It's a what?
Scalar quantity.
How do you know the scalar quantity? Remember, when we're doing scalar products, we have something A dot B equals to magnitude of A, magnitude of B, cos theta. If it will be a vector product, we have this. Scalar product are the ones that is have sin theta. And vector product, sin theta. But scalar product are the ones that is have cos theta. So they are scalar quantities and they are what? Measured in Weber. We measure them in what? Weber. So what do we use to measure magnetic field? That one is measured in what? Tesla. That one is measured in what? Tesla. But this was measured in what? Weber. Do you understand? Okay. So will you agree with me from here that a Tesla is still equal to Weber per meter square? Yes, because this is Weber, this is Tesla. If I divide both sides by A, it means a Tesla is still equal to Weber per meter square. So, yes.
If you don't use Tesla, you can use instead of using Tesla, you can use Weber per meter square. Correct?
Yes. Good. Now, flux is maximum when what? Flux is maximum when theta is equal to 0 degree. How do we know? By looking at the cos theta. There are two major numbers in trigonometry that shows extremities. What do you mean by extremities in physics? Maximum, minimum. Most times when they ask you what condition is a particular quantity minimum, you check that equation to ask theta or cos. So even if you never come across that before, just press sin 0 and sin 90. The answer is one of them. So in this case, I know that when I watch sin 0 on my calculator, I will have perpendicularity. Since theta is angle between the what? The normal and the magnetic field. And I will not want us to make a mistake. See, flux is maximum when theta is 0. When theta is what? So that means if theta is 0, that means I'm saying that the magnetic field is what? The magnetic field is what? Is perpendicular to the surface. Or you say the magnetic field is parallel to the normal. So that's it. So flux is maximum when theta is equal to what? I can't hear you. When theta is equal to what? 0. The meaning of theta being 0 is that there is no angle between the normal and the field. So it means the field is lying on the normal. The diagram becomes somewhat like this. This is the normal, and this is the field. There's no angle between them again. So you by yourself, in case you want to twist it, you know that when the angle between magnetic field and normal is 0, it places the magnetic field in a situation where it is now at 90 degrees to the what? To the surface. So anyhow you want to bring it out, anyhow you want to bring it out in terms of perpendicular to the surface, you know that perpendicular to the surface or parallel to the normal is where the magnetic flux will be maximum. Where it will be what? Maximum. You get it? But when is it 0? That's minimum. Flux is 0 when theta is 90. Press cos 90 in your calculator. It's not 0, cos 90. What do you mean? 0, right? That's what we're talking about. That's what I'm talking about. Because anything that makes us obtain is sin 90, cos 90. It means my magnetic field was parallel It means the magnetic field was parallel to who? Parallel to surface. That's as good as saying it was perpendicular to normal. I don't want any of this. We don't want any of this. We want to keep things on the maximum. Okay. Please, Mike.
Okay, so he said when the plot is maximum when theta equals zero. That is when the normal and the angle are in shape and no angle to it.
Yes.
So then as the plot is zero, when theta equals 90. I don't know.
When theta is 90, look at it. Remember that theta is the angle between the normal and the field. Normal cannot move. It's only this one that can move. This one can either move closer to the normal so that we can get a maximum flux, or it can move away and lie down. If it lies down, what angle is existing between him and the normal? 90. And that is where flux is zero. No, this other one. If this other one is saying this guy is standing in normal. So when he's standing in normal, there is no angle between him and the normal. And his angle is zero. Theta is zero for you to have maximum flux. Theta is zero for you to have maximum flux. Okay, so let's go. Okay, so flux can be positive or what? Or negative, depending on the direction of B and the chosen area vector. All right, next slide. Okay, magnetic flux density B. So now we talk about flux. Flux was number of lines. Abi? But look at what they will say about this one now. Magnetic flux density is what? Amount of magnetic flux passing per unit area normal to the field. Normal means what? Perpendicular to the field. Just what I was saying. So magnetic flux density is the amount of magnetic flux passing per unit area. Whenever you hear the word density, is divided by volume, area, or length. But in this case, we are dividing by area. It's called superficial. It's called superficial density. We call it superficial density. Okay? So, by definition, it means field or flux density is equal to flux over area. Flux over area. That's the meaning. These are the units area relationships that exist between them. Okay? So what is the direction? B is the vector, its direction is the same as H, which is a linear medium. Indicate.
This what you mean by linear medium?
Okay. You know that this one was when you get one test. Density is mass or a quantity present in a medium. That medium can be a volume medium, an area medium, or a length medium. So if I'm dealing with a volume medium, that's the normal density. If I'm dealing with area medium, that's a superficial density. When I'm dealing with a line measure, that's a linear density. So apparently, the magnetic field strength is a line measure. Do you understand?
Yes, sir.
Right. Okay. Common values, variability, permeability, and all this. Next slide. Okay. Magnetic field lines. So these are imaginary lines to represent the magnetic field. Imaginary lines to represent the magnetic field. Properties. They emerge from the North Pole and enter the South Pole outside the magnet. Why do we use the emphasize on outside the magnet? Because inside the magnet, the opposites are. Look at this. So this is not south. This is what's happening outside the magnet. Field comes from the north. Field comes from the north. Travels to where? When it enters inside the magnet, it continues. So when it continues inside, this is the direction of the journey of change. And when you look at it from outside the magnet, it looks like it's traveling from north to south. But when it enters through the south, it is traveling from south to where? North.
It's not like coming back to itself, or it's south, like they're trying to south and going back to the north.
The magnet did not move. Okay, good. The field comes from this north pole. When it comes out, it's going to want to go and enter into the south pole of any magnet around, or itself. When you enter the south pole, where you will be going. So that is inside the magnets, you will see a lot of magnetic lines that are traveling from the south to the north. So that's why I say internally, the travel is south to north, but externally is what? North to south. Emerge from the north pole, and then that's south pole, crossing the magnets. Inside the magnets, you go far, you go from south to north, like you cruise loose. The tangent at any point gives the direction of the magnetic field. No two field lines can intersect. The density of lines represents the strength of the field. Represent the density of lines. When you have a lot of field lines close to themselves, you individually increase the strength of the field. And that's what you see happening in solenoid.
Just to be sure, not to keep lying in that thing, meaning like not to like join each other, right?
Yes, no close. Do you understand?
Yes.
The density of lines represents the strength of the field. They tend to shorten due to tensions, along their length. That's it, due to tensions along their length. Alright, next. So, a magnetic dipole consists of two equal opposite poles separated by a small distance. It has a magnetic dipole moment. Okay? And pause. So, is it we can zoom in? Just shift this. Just go down like over. Yes. So magnetic dipole moment is a vector quantity representing the strength and orientation of a magnetic dipole. So what's the orientation? How are they arranged? How do they position themselves in free space? Very, very important. So they are expressed as what? IAN, where I is the current of the loop, A is the area of the loop, and this is the unit vector known to the plane of the loop. Now you see the magnetic field. This is precisely what the setup of a magnetic dipole moment look like. Alright. So you can see the dipole moment is like mass times this magnetic torque. Is that cool? Now, you see, this torque in uniform field, torque uniform field. Torque is equal to mass times magnetic field. Yes. Where angle theta is the angle between the mass and the magnetic field. Okay. Yes. So, magnetic field produced by currents. Magnetic fields produced by currents. The steady electric current produces a magnetic field. The steady electric current produces a magnetic field in the surrounding space. In the surrounding space. What do I mean? If you have a wire, we've demonstrated that already. When you have a conductor, anything now, that conductor, regardless of where current flows, if the current flows up or down, all you have to do is to position your hand right around it so that the thumb is pointing in the direction of the what current of the electric flow. Once you connect something like this, the remaining fingers are already showing you the direction of your magnetic field. That's it. The name of that rule is the right hand thumb rule. Please keep the name right. There's a difference between right hand thumb rule and right hand Fleming's rule. You know the same. So, superposition principle applies. And here, right hand rule stated it. So we look at this already. We have, I think it's this one. I'm going to the next. Good. So this was carried out by Hans Christian Ørsted, one of the greatest scientists that laid the foundational contribution to magnetic field properties. Now, he discovered that a current carrying conductor produces a magnetic effect. What did he do? He took a compass and placed the compass close to a circuit. I don't know. And what did he observe? When current flow in the wire, the compass needles placed nearby deflect its south, north, and south direction. It deflects their north, south direction. Influence magnetic field is produced around the current carrying conductor. So, thanks to Hans Christian, did a good job. Next, Biot-Savart law, one of the most important laws we will be using. One of the most important laws we will be using. Next. The magnetic field dB at point P due to a current element ideal is given by what? dB equals to this. Now, for those of us that have never come across this before, might be a lot of work for you today. We'll try to take the responsibility to make sure you know it today so that you can master it. So this is for a finite current carrying wire. We have this. So we're having this. All these things are the what parameters present in the equation. The change in magnetic field or the magnetic field at the point due to a current element. IDL. IDL stands for current element. That we took a small length of a conductor. We check. This is the unit vector for it. Observe it. Do you have? Because normally this formula can also be written in this form. I think that one is the best one. So permittivity of free space is equal to this. Current is equal to this. Then current element vector is this. Position vector from element to point P is this. This is the distance. Unit vector along between. So if I want to remove this is D. All I need to do is to integrate. Once I put integration symbol here, it helps me bring this from dB to B. So of course, if I integrated this, I'm integrating you know this, but we can't touch it this, and I'm going to integrate from here. Okay, to the next slide. Okay. Okay. So what these guys want to show me how they represent this is as position vectors. The position vector is a vector from the origin. So it shows its origin. They're trying to think that this R is of the origin. The origin, the I also of the origin.
Okay.
You get what I'm saying? So that's the major goal of that. Because so Ampere's circuitous law. So the line integral of magnetic field around any closed path is proportional to the net current enclosed. This looks like Gill's law. It looks like Gill's law. Ampere's law was the one, that's the law that's simplified by the Sabbath law. This is something we could understand. But then, so we have this, we have enclosed integral, so the line integral of magnetic field around any closed path is proportional to the net current enclosed. So this is the element of the net along those paths. Net current enclosed by the path A. So there are capability of free space. Yes? Okay. Now, if you do like this is not my integral. But if you do like this is an integral, or an integral means everybody like this is scattered. That's differential. Integral means bring all the scattered components and put them all together. But if I do not put an enclosure function, if I not do like this, then I'm not giving restrictions to how far you can gather. But if I do like this, I'm giving restrictions that, oh, maybe the gathering should be confined to this space alone. So, now this application is ideal for highly symmetrical situation, used to find good for long straight wires, solenoid, and toroids. What is what? It was symmetrical. I don't know, something that you can divide into two to see that it can have equal events. Like we human beings are symmetrical. You cut anybody like this, you have two event halves of the person. And it's very symmetrical. Oh, talk about it. They are different. Toroid is like a ring. Solenoid is more like a coil of wire. If I take wire and I want to increase the functionality of the wire, what I need to do is to roll it around the pencil and move it. That coil functions better than leaving wire straight. So key point, I have a method to calculate all those things here. Next. So for a long straight conductor carrying current I, the result of that Ampere's law will be this. Remember that the Ampere's law was showing us what? Was showing us this. This is what showing us. The moment we do this integral, this guy becomes what? this then becomes B times L because of mu I. Divided by L by L. Maybe we have equals to mu I by L. Now, what L is dependent on the magnetic field that being produced. So in a straight carbine, the magnetic field carries what shape? What shape do you see? Circle, right? That's the circle shape. So what is the area, or sorry, what is the formula for calculating the circumference of the circle? 2 pi r. That's why we have our lengths. That's why we have our length here represented as 2 pi r. So baseline equals to.
But now you use this formula to calculate amperes.
Yes, that's the amperes. This one is also the amperes. Okay. So I think you just need to remember that mu naught is a constant. So remember to solve questions. You will not be confused. So next. So we've gone past the normal line. Now we're looking at magnetic field due to the circular loop. Now this circular loop is similar to what we call a toroid. A toroid. It's not what we call a toroid. So magnetic field at the center of the circular loop. Now see something. This is a circular loop. Magnetic field leaves there. So at the center, what we observe is that this indoors mu naught I, and the field only travels 2 times the radius of that. So that's what we observe. That's when it's at the center. But at the point on the axis of the loop and distance S from the center, the expression becomes this. It's very difficult to remember, but you can always learn to do it. Okay, next slide. Now, sorry, we're going to do so magnetic field due to circular loops. Let me explain this. Okay, when you're having the solenoid, this is the solenoid. All these things are wires. It turns wires. So a very long wire now appears short called the number of turns. Now, whenever you do that, right, the solenoid is essential coil of n turns, length L, carrying current I. Once you do that, inside a long solenoid, you have this. But outside the laws of energy, the field is usually the words 0. Field will equal to 0. Yes. That's the same thing as saying, and you can see the proper toroid. When you run the wire around a ring, this is a ring, you run the wire around the ring. Do you get that? So, the major thing is, by looking at how we can calculate the magnetic field for each of these systems. The three important systems that I like to keep is the current carrying wire, the straight wire, the solenoid, the toroid, and that, you don't use it. So, that the toroid is what you just right? Magnetic pulse. Magnetic pulse. Magnetic pulses arise when moving electric charges or current carrying conductors interact with magnetic field. There is possible motion of charged particles and the operation of many electromagnetic devices. Key characteristics will depend on charge, current, velocity, magnetic field, and direction. Yes, and they always perpendicular to the motion or current in the magnetic field. It's very important. The pulse acts perpendicularly to motion in the magnetic field. So, these ones are given to us by vector products. Yes. Now, pulse. Pulse on a moving charge. Imagine you had moving charge. This is the charge here. And this charge moves in this direction of velocity. And the moving charge in the magnetic field experience the force that is perpendicular to both its velocity and the magnetic field. Situation: charge Q moving with velocity V in the magnetic field B. Angle between V and B is theta. Angle between those ones is theta first. Magnitude of the force is BBQ sine theta. Direction given by the right hand rule for positive charge. You see, reverse negative charge. So if you are dealing with a positive charge, please you use right hand. If you are dealing with a negative charge, you use what? Left hand. Now, your first finger points in the direction of the magnetic field. Where's your first finger? Points in the direction of the magnetic field. Your second finger points in the direction of the words. The second finger points in the direction of the velocity. And then your thumb points in the direction of the force. Okay. Your first finger shows the direction of the words. Velocity. Second finger, direction of the word, force. And your thumb is doing direction of what? Force. The what? The thumb alone is for force.
Okay, then second finger is for the
Yeah. Second finger is for your magnetic field. Right. So, let's see. And again, hold on. That equation that we did, they didn't name it. This equation is called the Laplace equation of magnetic force. The Laplace equation of magnetic force. Very important. So yes, we've done that. Next, the total force on a charge Q moving with velocity v in combined electric and magnetic field is called the Lorentz force. So you can see the combination of electric field and magnetic field here. The Lorentz force. The Lorentz force. And what does that help us do? Help us to observe particle acceleration. Help us to observe particle acceleration. Key point: Lorentz force combines electric and magnetic effects. Governs motion of charged particles in electric field, insertion of modern device, and technology. Okay. And just from this formula, I think if E is zero, if there is no electrical field, you just relate to what? B, V, Q. Right? It kind of reminds you of Laplace. Okay. So here now, force on a current conductor. A current conductor places the magnetic field, experiences the force. So the force it will experience is F equals to BIL sin theta. Both the BVQ and the BIL are both sin theta because they are vector modes. They are what? Vector product. Let me tell my students in my voice. I need to now. All right. So that's it. So you can see how we've been able to establish Laplace and Lorentz equation. We've been able to show how we link them. We started driving them from a bioservant, simplified it by Ampere's law. Ampere's law, we saw we could build them to what? To Laplace. Now, Lorentz. Lorentz is the one that is describing what? How a magnetic field can affect the what? Can affect the current carrying conductor. Bro, listen to me. So, so that's what we have there. Now, based on this and our description of vector analysis, right? When you see sine, what does it mean? We check out the angles, sine 0, sine 90. Which one gives us maximum? Maximum will give the one that theta will be 1. And then minimum is when the sensitivity was 0. So press sine 90 as 0. Even if it's not before, once you press it, you'll find out to be out. If you press sine 0, it will give you 0. Right? Good. So what does that tell you? It tells you that what? That sine 0 times since sine 0 is giving you 0. Then if you put it at 0 here, everything here will turn to 0. That means if you want to get the minimum magnitude of your Lorentz force, all you need to do is to make sure that the angle between your current conductor and magnetic field is what? 0. But to get maximum force, you make the angle what? 90. You get the gist? So that's how this works. So that's how it works. Okay, next slide. So you can see the notion. When we're treating Laplace, you saw the use of the right hand rule. When you use the left hand rule, when the charge is what? Negative. When you use the right hand rule, when the charge is what? Positive. Don't forget it. But back again to this. To use your Fleming left hand rule is different from right hand thumb rule. The one we used in Laplace was right hand thumb rule. The one we are using in Lorentz is Fleming left hand rule. This is what in Laplace, when we're treating BVQ, that's possible to BVQ. What we're doing there, we're using right hand thumb rule. Where our thumb was showing the direction of the force and all this thumb rule. We said if the charge on the limit is a positive charge, we use our right hand to orient. Well, of course, when the charge of the body was negative, we use our left hand to orient. But in this one, the name of the rule is Fleming's rule. The left hand rule is used there. So it is used to determine the direction of force. In Laplace, what part of the finger tells you the force? The thumb. But here, I'm seeing what gives you the thumb. Isn't it? Your second finger, your thumb, shows you the direction of the word force, the conductor. Right? Very important. But your first finger shows you the direction of the word magnetic field. Your first finger. Which is your first finger here? John. Okay. Where's your index? Where's your management finger? Where's the little finger? Drop your fingers. No, don't say you should drop your fingers. So, apparently, we use this to demonstrate first finger, second finger. I get it now. So, normally, if you are counting it in med school, you must stand oriented in a vertical position and you count from lateral to medial. You start from lateral to medial. It is used to detect the action of force on a current element of the facing magnetic field. Okay. Next. Now, stop. You know, we have two places we apply this Lorentz equation, two places in AC generators and motors. I follow what I'm saying now. So go back. If you are treating generators, I get it now, you use your left hand rule. If you are treating motors, you use your right hand rules. Okay, I'm going to use an example. Go to the next slide. I use one example slide. See this. I see. Now, this blue line is showing you the direction of your field. I see it. It's showing you the direction of your field. And this here is your wire, the conductor. But I'm not using this up one as the case for you. But that is going to be rolling and cutting across the magnetic field lines. Good. Now, I want you to place your hand in such a way that now I'm using your left hand. I want you to place your hand in such a way that your this finger is pointing in the direction of the field. Right? Good. Then I want you to also send your hand, this finger here, to face the direction of the wire. See the wire there. Now it's because, the road is not drawn this wire is looking like as it is like this. So it's like me putting my hand like this. The field is better like this. This finger is pointing into the page. Just like that. So maybe you see the force down there. Just like what I'm saying. So that's it. If there will be a motor, the same application we are using your right hand. Now, yeah. Forget about the other finger. I need you to want to both these two. This one points in the magnetic field. Then this one points in the direction of the conductor. Where the conductor is facing. So now you have to make that one. See the conductor there. The wire is doing as if it's pointing into the page. As if it's pointing inside the page. You know, you can't draw inside the page. So this is what it looks like inside the page. So I want you to fix this one so that it's pointing in that direction. And this one pointing in this direction of you. See, this one is pointing in the direction of the female. But if you are not causing this because you are still facing like this, how about you do this? Gentlemen, this one is pointing into the page. So like this. So release your tongue. You see your tongue is facing. That is really what we act. Gentlemen.
Yes, sir.
No, this is not already done now. No worries. No worries. we talk about the lab and probability. Potential energy is online. Okay, this is what this is what the magnetic level field from South Pole to North Pole of the universe. Okay, next slide. These are some questions we're answering them here and now. So let's start with the first one, please. Let's do the weather. Let's zoom please. Okay, that's too much of zoom. Very good. Now, listen. A proton with velocity 2.0 times 10 to the power 6 meters. You see, in physics, what you used to tell you is immediately as things certain things, you start picking up on the what? On the parameters. Start picking up on the parameters. Take the parameters B, so we can work on them visibly. You understand that? Okay. Okay. So everybody will hold together at the same pace. Read the first question out clearly and audibly. First question.
It's 2.0.
Thank you. So this answer is what? Velocity. Correct. So we're always going to record that the velocity is 2.0 times 10 to the power what? Meters per You know the meaning of Tesla? Tesla is used for magnetic field. So the B is equal to what? 0.50 Tesla. Okay. Now, another rectangle, is it going to be giving us maximum force or minimum force? Maximum. Remember, I said it. Is when anything sin theta is 0, that it becomes minimum. But now they're giving us 90 degrees. Sin 90 is 1. So we're going to be experiencing maximum force. Alright. So yes. Find the force on the proton. So the next one to see is Q. They're giving you the Q value. But the Q value is something more. It's 1.6 times 10 to the power minus 19. Just put it here. Take Q as 1.6 times 10 to the power minus 19 column. So yes. So what formula comes to our mind? Is it Laplace or Lorentz? Laplace. So we're looking at Laplace force here. F equals what? BVQ sine theta. Our theta is 90. Because the theta is there. Perpendicular at 90 degrees right down. F is 9 equals to 0.50 times 2.0 times 10 to the power 6 times 1.6 times 10 to the power minus 19 sine 90. When you put this in calculator, what does it give you? 1 point what? The third one. The second one. An electron moves with the velocity of what? Parallel to what? Do you know that? For this, do you really need to solve? Do you need to solve? You don't need to solve. The answer is 0. Because they said parallel to what? Magnetic field. So you know already that once they parallel, that's 0. Because parallel is 0 degree. Sin 0 is 0. And cancel out of it. So I believe you understand this now. 1, 3.
The conductor of the 0.2 meter carries a current of 5.0 amperes and is placed in a magnetic field of 0.40 Tesla, perpendicular to the field. Find the force.
Now I'm going to do my business. What the regular is meant to do. So, continue.
Find the force on the conductor.
What formula are we using? BIL. Yes. Yes. So this is Lorentz force. Lorentz force. So can somebody solve that with much time? 0.2 meters, it's better like 0.4. I think I've worked with 5 and 0.4 2. And now it's 0.4. That's a 0.4, right? Very good. Look at this number 4. What's the number 4? Number 4.
Carrying current to the right, the magnetic field directed into the page.
Just another thing. Calm down, breathe. State plane's left hand rule. That first statement alone has only made you understand that you are working with Lorentz force. How? Because it's Lorentz force that we used right hand rule. Flame. Also, we use Fleming's right hand rule. Right? Now, state Fleming's right hand rule and use it to find the direction of the what? Force on a what? Conductor. Carrying what? Okay. So, current is going to the where? Right. And when we say current is going to the right, that's like the wire, where the wire is pointing, when it is flowing to. So, so now I have used it to find the direction of force on the conductor carrying. So what else do you have there? Magnetic field directed into the page. Into the page. You understand the meaning of that? Magnetic field into the page. Current to the right. So we are trying to look for where our force will be. Without checking much. Thank you very much. Our force will be down. Because we know that these 3 forces must be perpendicular to themselves. Yes, you can do it like this. But you yourself, if you know you've not mastered it, you have to still use the right hand rule. So what will you be doing? Put your left hand rule, orient it the way I gave you that time. Like I'll be in the for you. So this one is for which one?
For the direction of current.
This one is for which one?
So it's for the current.
The magnetic field. Wait now, come down, not here. Let me join. This body, this is what it looks like. This one's for the current. And this one to the page. See, good. To the page. No, no, let's you see it. Do you understand? Correct. Into the page magnetic field. Force. You see it. That is how it works. So a square current loop of side 10 centimeter carries a current of 20 or 2.0 amp and is placed in the uniform magnetic field of this. If the plane of the loop is at 60 degrees to the field, find the torque on the loop. Whenever I see this kind of thing, like just remember how many tons? Does it have many tons? So mu n I mu n over n. That's all there. Right. So next slide. The meaning is all those remaining down. Magnetic properties of materials. We've discussed this already. Discuss this. Okay. We've actually discussed this. All this diamagnetism, ferromagnetism, we've done them already. Which one gives weaker repulsion? Paramagnetism. Which one gives weaker attraction? Diamagnetism. Which one gives strong attraction? Thank you, ferromagnetism. So welcome to electromagnetic induction. Electromagnetic induction. We are literally in number 27. Yeah, number 27. So I'm definitely sure we are achieving this eventually. We'll finish it. Okay. So, electromagnetic induction. This thing is the process of, or should I even use the word? It has to do with producing EMF in conductors when the flux linking the conductors change. So whenever we express a change in flux, listen up, the drivers of electromagnetic inductions is flux. Do you remember flux? What are flux? What's magnetic flux? We're talking about the number of the lines present on it are acting towards the surface. Now, if that number of lines acting towards a surface change, that change sometimes can cause or induce a reaction. It can induce an electromotive force on the conductor. And you know what that electromotive force does? What does it do? Have you heard of electromotive force before? What's the meaning? It generates a potential difference in what? In a closed circuit, in an open circuit. A circuit where current is not even flowing. There is now potential difference. That's what it does. That's the major difference between electromotive force and your general potential difference. People say it's the same. They are not the same. They are not the same. All right. Electromagnetic induction is the production of an EMF in a conductor. It's the production of what? In a conductor. When the magnetic flux linking the conductor does what? Changes. And what causes this discovery? It's observed that when you move a magnet in a specific orientation into a solenoid, you find out that there is usually sensitization on this here, which gave insight that that process usually caused a generation of current. It caused generation of PD, because PD is what drives current. If there's potential difference, there's a large potential difference, current will want to flow, charge will want to move. I get me now. Charge always want to move from lower potentials towards higher potential. So when we have a system that has established that, current start moving. You understand? With generation of current. So we're saying whenever the magnetic flux this through a circuit change, an EMF is induced in the circuit. The induced EMF exists only while the flux is what? Changing. The phenomenon is the basis of generators, transformers, inductors, and many devices. Factors affecting the induced EMF. Rate of change of flux. That is change in flux over what? Time. That's one of the factors that affect the amount of induced EMF. Another thing again is the number of turns in the coil. This coil, the number of turns. Orientation of the coil related to the magnetic field. And then area of the coil. All of these things are things that can affect the induced EMF. Okay, next. So Faraday's law. Faraday's law. Faraday's law. According to Faraday discovered that the induced EMF depends on how the magnetic force changed with time. Already, we've seen that it is the change in flux that will induce an EMF. But now, how the flux changes with time to produce the induced EMF is what Faraday was studying. First law, whenever the magnetic flux linking a circuit changes, an EMF is induced in the circuit. Second law, the magnitude of the induced EMF, that's the size, the amount of the induced EMF, is directly proportional to the rate of change of the flux, of the magnetic flux. I get what I'm saying now. It's directly proportional to the rate of change of the magnetic flux linkage. Are you getting this now? So that is the expression I'm saying. Where is the induced EMF? So I'm saying that E, which is the induced EMF, is directly proportional to the what? To the rate of change in flux. Directly proportional to the rate of change in flux. And then there is this negative sign here. The person that explains that negative sign is Lenz's law. And we'll get there. So the magnitude of the induced EMF is directly proportional to the rate of change of the flux. A higher rate of change of the flux will create a higher EMF. If n is constant, I hope you know what n is. N is the number of what? Turns. N is the number of turns. And it's meant to be constant. Next. Lenz's law. Let's not determine the direction of the induced EMF and current. You know, I told you that once EMF has been established, potential difference has been established. And once potential difference is in game, current is going to flow. It's just like temperature. Heat flows when there is a temperature difference. So who do you think is the driver of the heat flow? Temperature. The moment one layer of this plate is very hot and that place is very cold, that will trigger heat flow. You understand? The same way it is with currents. If one place has a very high potential and that place has a very low potential, that will want current to flow from the low potential to the high potential. So Lenz's law determines the direction of the induced EMF. And what does it state? The induced EMF is in such a direction that it opposes the change in flux that produces it. When we say the induced EMF, it's almost the same thing as saying the current produced by the induced EMF as a result of the change in flux. I get it. So we said the induced EMF that produces the current is in such a direction that it does what? Opposes the change in magnetic flux that produces it. That means in this formula here, that's why we're having negative E. But this induced EMF is acting in the opposite direction to the flux. Let's mention now, watch. Nature naturally opposes the causes of change spontaneously. Not the spontaneous thing. Nature affects the what? Nature affects the what? The causes of change. And then, if flux increases, you know what I'm talking about, Abby? The magnetic flux. If flux increases, whether increase or decrease, once flux change, what are we expecting? Induced current. It's better you call it induced EMF, which now produces the current. So once flux increases, there is an induced EMF that is producing what? A current. Are we together now? And that current opposes the changes of the magnetic flux. Thank you. You're really getting it. So it's that simple. So if flux decreases, induced current creates a field that opposes the what? Decrease. If the flux increases, induced current creates a field that opposes the what? Increase. It wants to start fighting against that increase. It's just like the Chatelier's principle. So we have two kinds of induction. How many kinds of induction? What are the two types of induction? Self-induction and mutual induction. When we say we're doing self-induction, that means it is your own coil and your own system that your own flux, the flux in the particular coil is what changed. That change is now affecting or generating a EMF in that same coil. I get what I'm saying? Good. That one is what self. But when the flux change is generating an EMF in another coil, I get to know another one. That one is mutual.
And the change in flux creates an EMF in that same coil.
Yeah.
That is self.
That's self, yes.
If the flux changes now and the EMF is created to
another coil, yes. Mutual inductance. You get the gist. Self-induction is the production of EMF in a coil due to changes in the same coil. Remember when they mentioned EMF, what is getting produced also? Current. self-induction. Self-induction is the production of what? Of an EMF in a coil due to a change in the current in the same coil. A changing current produces a what? A changing current produces a changing magnetic flux linking the coil itself. This changing flux induces an EMF in the same coil, opposite the change in current. So you consider that thing like a cycle. You changed, and because you changed, I changed, and I made sure my change is occurring in such a way that it will change you back to what you. When it changes you back, you too not change again. And you understand what I'm saying? It's like a cycle. You get? That's how it is, like a cycle. So this is the expression. This is the expression. The negative sign you see here is due to what? Lens block. And the EMF, the induced EMF, will produce a current that acts opposite. I get what I'm saying? That's it. One on go. So, induced EMF is equal to the I. Now listen up. L is the magnetic flux. Sorry, L is the self-inductance. It's the self-inductance. Now, a very important point to know that the self-inductance depends on what? It's important for us to know that what? The self-inductance depends on the number of what? Turns. Depends on the number of turns. It must always be there because of Lenz's law. No, this is the expression already. So we're working with the negative. From there, the negative is corrected. So, what are the factors that affect self-inductance? It depends on the number of turns, area, length of coil, core materials. In the opposite the change in current. Okay, when we now go into this, we are looking at mutual induction. You can see two coils. Mutual induction is the production of an EMF in a coil due to a change in current in a nearby coil. So a production of EMF in one coil due to a change in current in another coil is what is going on in EMF. We have a change in flux in one coil, it causes a change it generates an EMF in another coil that produces a current, right? Now that activity in that coil is now also making sure that its current propagation is causing an opposite change in the other coil. So it's like a cycle. So look at it, a changing current in coil 1. A changing current in coil 1 produces a changing magnetic flux. Now that changing magnetic flux, it's producing a changing magnetic flux in that same coil 1. That changing magnetic flux, part of that flux links coil 2. And now the change in flux linkage in coil 2 induces an EMF in it. That's what I'm trying to say. Yes. So change in flux linkage in coil 2. I've said that. So how do we represent it? Mutual inductance is represented with cathode M. Represented with M. So we know it is all about the flux and the currents. So first thing first, this is an induced EMF in coil 2 will cause or create a current in coil 2. EMF change in coil 2 will create a current in coil 2. That current in coil 2 will cause a change in what flux in coil 1. And when there is a change in flux in coil 1, that will cause a change in the EMF in coil 1. It's a current that will be causing or inducing an EMF. You understand? So it's a similar sort of thing. So, well, that's the situation of things. That's the situation of things here. So, you can see this now represented self-indulgence or mutual indulgence. We say, you know that E is equal to negative M Gi over dt. You get that? So when you see us write pi 2 1, it means where phi 2 1 is the flux through coil 2 due to current in what? Coil 1. Did you get what I just said? So interpret this mutual inductance relationship. You know that mutual inductance now is equal to N2 theta 2 1 over I1. What is this statement? No. That thing is not a number. It's a relative explanation. That's what I was explaining when you on this. I'll repeat it. See, when you see them write all those numbers, like something like this, it means flux in what? Flux in what? In coil 2, that is as a result of the current in when? Coil 1. So if I want to do mutual inductance, I can write N2 theta 2 1 over I1. Why am I not writing over I2? Because the current initiated this thing in this coil 2 was the current that was produced in coil 1. So this statement means number of turns in coil 2 multiplied by the flux through what? Coil 2 that was due to a current change in what? Coil 1. So obviously divided by current in coil 1. That must be equal to number of turns in coil 1 multiplied by the flux that was through coil what? 1 as a result of the change in current in which one? Coil 2. So we have to divide by what now? By current in 2. Okay. Next. Now we're looking at edges current transformers. Edges current and transformers. Let's start with understanding the transformer because this edge current, you need to understand where I'm coming from. Edge current. Now, a transformer is a device that transfers what? AC electrical energy from one circuit to another through mutual induction. It's an application of mutual induction. So all those changes in one flux in one coil as a result of all those something in one coil is all what happen to transformer. So what are the things I want you to observe here? You notice in the transformer, you have this plate, true of us. Then around it, you are seeing this coil. When you are seeing coil, I mean. Now, a transformer can be step-up transformer, can also be what? Step-down transformer. If the number of turns in the primary is greater than the number of turns in the secondary, this is the one you will connect to have. The one here is the one you connect to yours. The one here is the one you connect to the source of power, maybe from down. I can't do that. Yeah. Yeah, you see 220 something volts. That's when I want into your house. You connect this part to your house. So if this part is more than this part, the step-down transformer. But if this part is smaller and here is more, the step-up transformer. Okay? Can I? Okay. Now, if you look here clearly, notice, I don't need to count, but like, there are more number of turns here, like turns, than here. What those turns do is, they decide if the transformer is step up or step down. If the number of turns in the secondary coil is greater than the number of coils in the primary coil, then that is a step down transformer. Before it can be a step up, that is, we want to create a situation where we want to supply you more power. We want to supply more power. Okay. So, when a conductor experiences change in magnetic flux, circulating current are induced to the bulk of the conductor. They are called edges current. So listen, you have a conductor experiencing changing magnetic flux. Circulating current around the core But this thing is called a core. Separate current around the core. Induce. They are induced within the power of the conductor. So those things are called eddy current. Normally we would have wanted the current to be confined to a specific part, but no matter how precise you are, it still is eddy current. So what does eddy current do? Causes loss of power, reduces efficiency of the device. Because many unwanted current moving around your core. Do you get it? Before we wanted only induced current. No. So see eddy current in a solid core. I see eddy current in between the core. This is not to weaken the what I call it again. This is not to weaken the core. See the laminated core. So one of the ways to prevent eddy current is to laminate the core. Lamination is like protecting the outer surface of the core. So you have the material is fits to the outer of the core, thus current can just easily move on it. So we use high resistive materials like silicon, steel, or ferrite. Why would we use this? Because we want to make sure current don't pass anywhere we don't want. The current only how to pass a specific place. That's fine. We don't want current to be passing, just moving in and around the core. So, I did transform relationship. Because I don't reach again. Yes. Depending on the question they ask you. One thing I need to know is that power is conserved. The power in the primary coil usually is equal to the power in what? Secondary coil. And power is energy. So what's that? I1 V1 is equal to what? I2 V2. You see that? So that's that. That's that. Okay? Okay. What is it? All right. So move to the next slide. That's the last slide. All right. Very good. Think I have 5 minutes more to get a bit of rest. Road. Overcome. Before then, ask questions on what we've done. You want to respond. In the next 5 minutes, you have a short break. So, who can explain to me what we meant by mutual induction? What do you mean by mutual induction?
Mutual induction, that is the when there is a change in magnetic flux in a coil, it creates an EMF in that coil and affects the second coil that EMF in second coil.
Mm-mm.
That's why the magnetic flux for the second coil.
Good. By generating the what? What do you consider it?
Current.
Thank you very much.
And also it goes back to the exercise.
Okay. Thank you very much. Give the mic to anybody like
Take that.
be specific, just give us. People set your score. Set your score later. Okay. So can you just state the formula? What is the formula? Formula for Laplace force. And you know that radioactive is nature. Okay, just briefly discuss with me anything you understand about magnetic induction. Where is the mic? Good. 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 So what is changing magnetic? Well, what do like this? What do you like fashion? Come on. Tell me everything I need to know about Laplace and Lorentz force. Understand that Laplace force and Lorentz force. What do you understand about it? What do you tell me about Ampere's law? Biosavant law. Magnetism, magnetic materials. What is diamagnetism? What set of magnetic materials return weakly? What magnetic materials? Magnetic materials. What set of magnetic materials have weak repulsive action? Weak repulsive. Okay. What are antiferric magnets? Okay, briefly discuss everything you know or what you meant this class. Prove to me you benefited. You're sleeping before the go. Alright, so you guys have 5 minutes to stretch. system. All right. So we're going to be treating AC circuits. But before then, I want us to solve a number of questions on what we've done previously, as on magnetic force to magnetism. So a number of questions. Yes. Was your understanding of magnetic force, magnetism, in the current current conductor is very important as it will be applied in AC circuit as an alternative current. So, do well to participate actively in this question and answer session. Okay. So the floor is very much open to interactions, and when we're stating some MCQ questions, which are A-level standard-based questions actually. So you will ask for questions, and I'll mention names. What's the name? What's his name? Are you okay if I mention your name? Okay. All right. Question 1, please. A proton enters a uniform magnetic field perpendicular to the line, to the field line. The force acting on it is dash. I said a proton enters a uniform magnetic field perpendicular to the field line. Enters the uniform magnetic field perpendicular to the field lines. The force acting on it is dash. A, parallel to the field line. B, opposite the velocity. C, perpendicular to both velocity and the field. And D, 0. Yes. Now, that question is reminding you of your right hand rule. All hands, all fingers, the position and oriented perpendicular to themselves. So your velocity, right? Your velocity and your field, they all acted perpendicular to themselves, 90 degrees. So the force acted perpendicular to them, to both of them. Understand? So the correct answer to that question is supposed to be what? No, perpendicular to the both velocity and field. But see, this is the force. I get it now. You get it? Alright. It's very okay. So the SI unit of magnetic flux density. The SI unit of magnetic flux density is what? Let me give her the mic. The SI unit of magnetic flux density is what? A, we have Weber. B, we have Tesla. Azure, Gilbert. The magnetic flux density is measured in Tesla. That is wrong. Are you confident? That's correct. Okay. The magnetic force of the moving charge is maximum when the angle between velocity and magnetic field is dash. A 0, B 30, C 16, and D 90. 90 correct. So when you have your magnetic force maximum with the angle between velocity and magnetic field at 90 degrees because of the sine theta. So the force on a conductor carrying current is dash A BIL, B BI over L, C IL over B, D BL over I. Thank you very much. Please next time use the mic. Okay, question number 5. The direction of force on a current carrying conductor is determined by dash. The direction of force on a current carrying conductor is determined by dash. A. Fleming right hand rule. B. Fleming's left hand rule. C. Right hand top rule. And D. Lenz's law. What's the answer to that question? Left hand rule. Very good. So left hand rule is for motor, right? The right hand rule is for generators. Thank you. A charged particle moving parallel to magnetic field line experiences dash. Please pay attention. I will start calling names. And remember you are live. The parents can be watching. So the question says, a charged particle moving parallel to magnetic field lines experiences dash. A. Maximum force. B. Zero force. C. Half maximum force. And D. Circular force. Yes. Titi. You might like.
Zero force.
Very, very good. Zero force. Because we said it. Once the charge particle, but what we'll do is Titi will be like, Titi will not call the answer. You will be able to choose the next person to answer this question. Just give the person the mic. So, a charged particle moving parallel to the magnetic field line experiences zero force. So the next question, if anybody, quick, very good. The magnetic field inside a long solenoid is dash. The magnetic field inside a long solenoid is dash. A 0. B, uniform. C, circular. D, random. What's the answer?
Uniform.
Why? If I may ask. The reason. Why? Anything you are not good, that's by. See your mind, comfortable. Because what? You are correct. Understand? But when you have watched before, the lines are not intersect. Okay, so give me the mic. I like the fact that I'm able to respond better. So, magnetic field lines never dash. A, intersect B forms a loop. C, enter south pole. D, leave north pole. Magnetic field lines never dash. A, intersect B forms a loop. C, enter south pole. D, enter north pole. That's a very good. My next. People are rejecting mics. Number 9. The magnetic field due to a long straight conductor decreases with dash. A magnetic field due to a long straight conductor decreases with dash. A, R squared. B, R. C, 1 over R. D, 1 over R squared. Should we have why? Well, that's not correct. The answer is supposed to be decreases with 1 over R. Where did you get the equation from? From Ampere's law. B equals to mu naught I over 2 pi R. That's simple. Okay. Number 10. Who is answering that? The force between two parallel currents carrying wires carrying current in the same direction is dash. Okay, so on the mic. The force between two parallel currents carrying current in the same direction is dash. A, repulsive. B, attractive. C, 0. D, alternating. The force between two parallel current carrying wire, right? Carrying current in the same direction is dash. A, repulsive. B, attractive. C, 0. D, alternative. 0. No, wrong. I was expecting you to just do it attractive. When the direction of the wire, the current flow in the same direction between the two parallel wire, attraction happens. But when you go in opposite direction, you have two wires. Current is flowing up in both. what we experience is what we experience attraction. But if current was flowing down the black one and up in this one, that's oppositely, what will be happening is repulsion. Do you get it? What will happen is repulsion. Okay. Did you do something just now? Good. An electron enters, an electron enters a magnetic field perpendicular to its velocity. An electron enters this magnetic field perpendicular to its velocity. Its path becomes A straight line, B a circle, C a parabola, D an ellipse. An electron enters a magnetic field perpendicular to its velocity. Perpendicular to its velocity. Its path becomes what? And then straight line. No, that's wrong. It's not straight line. Let me show you something. No. Just imagine. Do you know that magnetic forces, when an electron enters a magnetic field, sometimes what the magnetic field does to that electron is it causes it to start rotating. Because the field itself is what? Spherical sometimes. So that rotating, when an object is moving in a circular path, what force does it experience? Centripetal force. Right? Yes. Now, then you can say that there are some conditions where magnetic force induces centripetal force for a charged particle. So I'm having B VQ equals to mv squared over r. Just what I just did now. The energy over r is what? Centripetal force. Who causes the centripetal force? The magnetic field. V can cancel one of the V and let it one V. Let's make V the subject of the formula. What do we have now? dqr is equal to mv divided by m. dqr over m. That's the relationship. So they ask you, calculate the velocity of an electron in a magnetic field. Just know that velocity. That's it. Okay. The radius of circular motion of a charged particle. Who is in this question? Yuri. The radius of circular motion. The radius of circular motion of a charged particle in a magnetic field depends directly on the radius of the circular motion. From here you can know, because this equation can from here get the radius expression. So the radius depends directly on, when I say directly, that means which one is directly proportional to. And the ones they will directly proportional to are the ones in the numerator. After I have made it the subject of formula. A, magnetic field. B, charge. C, momentum. D, electric field. magnetic field. B, charge. C, momentum. D, electric field.
Magnetic field.
Magnetic field. Use the marker. Go and make the subject of formula. Should we that's what I'm supposed to do first?
Yes.
Do that in your book. Thank you very much. MV over what? Big Q. So your answer was incorrect. Because we asked for the one that is directly related. And I told you directly and what's in the numerator. So it's B in the numerator. So what's the answer? Thank you. Because mass and velocity is momentum. So that's how you're supposed to approach that question. Cyclotron frequency depends on dash. Cyclotron frequency depends on dash. A. Speed. Now, to get to cyclotron frequency from here, what you just have to do is you have to remember how to re-express V in terms of angular velocity. You know the formula that links angular velocity with V? That is V is equal to angular velocity R. If you put that here, what will it become? Angular velocity R will now be equal to all those things, Abi. See what I'm saying? This V now, I say record that V is equal to what? Angular velocity R. Angular velocity R equals to V equal R over N. R cancels R. I'm left with this. Do you see that? So I believe in this place, what you can see is charge towards mass ratio, right? Charge to mass ratio. So what will be your answer? A speed, B radius, C charge to mass, and D magnetic flux. Charge to mass. This question is for you, Titi. The work done by a magnetic field on moving charge is dash. The work done by a magnetic field on moving charge is dash. A, positive. B, negative. C, 0. D, infinite. What's the answer? Positive. No. The work done by magnetic field removing the charge. The answer is supposed to be 0. It's supposed to be 0. And that's because the magnetic force is always perpendicular to the velocity of the particle. And for the fact that force is always perpendicular to the velocity of the particle, you know that work done is force and distance cos theta, normal work done. So if you put in that theta 90, I just told you the measure. Because 90 is what? 0. And that gives you a work that is equal to 0. So, alright, let's go on. Magnetic force changes dash A, speed only, B, direction only, C, mass, D, charge. What's the answer? Magnetic force changes dash A, speed, B, direction, C, mass, D, charge. Well, what's the answer? Direction is a force, is a vector. And it changes only the direction of motion. The speed remains constant. Magnetic flux, not flux density. Magnetic flux is measured in dash. A, Tesla. B, Weber. C, N. D, volt. Weber, correct. So, next one. Magnetic flux is maximum when magnetic field is dash. Magnetic flux is maximum when magnetic field is dash. Be very careful. A, when magnetic field is parallel to the area. B, when it's perpendicular to the area. C, when it's 0. D, when it's tangential. When it's 0, no. What was the answer? Thank you. You know, we're explaining that day. If you say, look at something. It is perpendicular, I can understand why you must have said 0. 0 is still correct. But we did not tell you 0 to real. You know, when it is 0 to normal, that is when it is also still maximum. Right? So that's why you probably say 0. That's why you probably say 0. Or you're supposed to be more specific. Magnetic flux through its surface is equal to dash. Magnetic flux through its surface. Magnetic flux through its surface is equal to dash A. Magnetic flux equals to BA cos theta, B, BA sin theta, C, B over A, D, AB squared. I didn't hear you. BA cos theta, very good. Increasing area. Increasing area. Increasing area. Increasing area while B remains constant causes magnetic flux to dash. A increase, B decrease, C remain constant, D becomes 0.
Increasing area.
Yes. Yeah?
Increase.
I didn't hear you. It was an increase. Good. Correct. So, because we know that it is proportional to B and A. 1 Weber is equal to dash. 1 Weber is equal to dash. A, 1 Tesla per meter. B, 1 Tesla square meter. C, 1 ampere meter. D, 1 volt. Time is going. 1 Tesla. 1 Weber is equal to 1 Tesla. That's wrong. Who can help us? Nobody can help us. So it's not equal to 1 Tesla. There's no option set like that here. All we have is 1 Weber equal to 1 Tesla per meter or 1 Tesla square meter. Okay. It is actually 1 Tesla square meter. Okay. Number next. Okay. The magnetic field around the magnetic field around a straight conductor forms dash. The magnetic field around a straight conductor forms dash. The magnetic field around a field conductor forms dash. A, straight lines. B, circular lines. C, ellipses, and D, spirals. Straight lines. Do you remember that experiment where we hold something like this and this is the magnetic field?
Okay.
What line is that formed? Circular line. That's it. Circular line. Why did you say straight line initially? Next. The right hand thumb rule gives dash. The right hand thumb rule gives dash. The right hand thumb rule gives dash. A, force direction. B, current direction. C, magnetic field direction. D, electric field direction. What's the answer? Very good. Magnetic field direction. Very, very good. Okay. Let me sleep now. Let's not come and check the laptop. All right, let's go on. Let's go on. Question number 23. Doubling current in a straight conductor. Doubling current. Doubling current in a straight conductor causes magnetic field to dash. Causes magnetic field to dash. A, have. I think it's showing something. I'm not sure. Like I'm showing, like it's showing something. I want to be sure that it's fine. The timer. So, doubling current in a straight conductor causes magnetic field to dash. A, half. B, double. C, quadruple. And D, remain constant. What's the answer? Whose question is that? So we should wait at it. remain constant. So if you double the current, the magnetic field will remain constant. Can you prove that out for me? The question is double current in a straight conductor causes magnetic field to dash. A half, B double, C quadruple, D remain constant. She said remain constant. Can you prove her wrong? There's an equation that I need you to just mention. So that you can use the equation and just know. The Ampere's equation that says magnetic field is equal to what? Mu naught I over 2 pi r. You can see, if you double the current value, what do you think will happen to the magnetic field eventually? To double. These are simple questions people miss. Okay. Ampere's law relates magnetic field to dash. Ampere's law relates magnetic field to dash. A, voltage. B, electric charge. C, current enclosed. D, resistance.
Current enclosed.
Thank you very much. I appreciate your answer. Electric motor operates mainly because of dash. A, electrostatic force. B, magnetic force or current. C, gravity. D, capillary action. Should I come again? Electric motors operate mainly because of dash. A, electrostatic force. B, magnetic force on current. C, gravity. And D, capillary action. Really? Electrostatic force? But you forgot that we used electromagnetism for motors. Okay, the correct answer is magnetic force. Alright, so we are going to be going into AC circuits. Just now. Outline now. We are about diving into a very new concept, which is AC circuits. AC circuits. AC circuits. And that's what we're looking at. A special type of current that is sinusoidal. We call it alternating current. All along, we've been dealing with circuit diagrams where we get our power source from batteries. This time around, we want to utilize alternating currents. what are the things we are going to be exploring in AC circuits? This is module 28. Let me write it here. Module 28. Outline, we're going to be introducing you to the concept of AC circuits. Then we'll be looking at RMS values, both voltage root mean square and current root mean square. We're going to also be looking at peak values. We'll be looking at AC circuit containing single elements. After which we'll look at the RLC series circuit. Are we there now? That's what we're talking about the different reactants that we have. Also within there, we'll be looking at impedance. We'll also talk about RLC series resonance. Of course, we'll dive into power in an AC circuit, and then we'll treat RLC parallel circuits. So, without wasting much of our time, we'll dive right in. So, first thing first, what is an alternating current? What is an alternating current? In alternating current, which is AC, the flow of electric charge periodically reverses direction. Unlike direct current, where the flow of electric charge is only in one direction. AC circuit is not channeled in one direction for the all through. It's periodical. It's sinusoidal. That's why you see it. It starts from an equilibrium point. It moves. It goes up. It moves. The light is always fluctuating. Alternating current is your normal power light. Let me just use the word general NEPA light. It works with AC current. And that current is not stable. It's always fluctuating. Periodically is an example of a periodic motion. It's an example of a periodic motion. So the first thing I want to look at there are root mean square values. Root mean square values. So when you hear the word root mean square, we are talking about what? We are talking about the average. The average. We are looking at something more average. An alternating voltage or current is current voltage which is an oscillating function of time. So if you want to express them, you literally have to express them as a function of time. Why? Because they change every single time. The current is fluctuating, the voltage is fluctuating. And you ask yourself the question, what is this V naught? The V naught there stands for peak. So we are talking about amplitude. When V naught is the amplitude of the voltage in the volts, F is the frequency in hertz. And we just put this there for you to remember. That angular velocity is 2 pi f. So you should know that. Meters in AC circuit read the effective or root mean square value of the current and voltage. When I say you read the root mean square, it means that you are reading something that looks more like an average. Listen carefully. And these things they relate in this form. These are one of the formulas you are going to be needing in this course. So you're going to be needing this. V is equals to V naught sine angular velocity t. You're going to be needing this. You are also going to be needing the fact that your VRMS is equal to your V naught over square root 2. The same thing for your IRMS. Equals I naught root 2. It's very rich. Let's move on. If I may ask you, in Nigeria, the frequency of light, the frequency of power that Nigeria supplies is what? It came out last week. What's the frequency of the current or the power that Nigeria supplies? Alternate current. The NEPA light is what frequency? In hertz. What does it mean? Is in hertz. This is mine.
I don't understand your question.
Now, Nigeria supplies you light because you're Nigeria. The frequency, you know, we said something earlier that AC circuit, that is normal NEPA light.
Yes.
These lights are not just lights that propagate singly just one direction or through. It is repeatedly moving up, coming down. It's a periodic motion. I get you now. So I'm not asking you the frequency which describes the number of cycles per second is how much in Nigerian lights? It's 50. Last year, the light acquisition with you. Is that mean 50? 50 hertz. Who can tell me the meaning of that? It means that our light reverses 100 times every second. The power reverses 100 times every second. Do you see how many reversals happening in just 1 second? That's why you don't notice it. It's extremely fast. You can't capture it from the ball. Do you understand what I'm saying?
Yes, sir.
Extremely fast. That's why you can capture it. In US, it's 60, which is about 120 reversals in 1 second. So you should know that shows higher quality of light. Right? Good. So, they can ask you, what type of waveform is seen in alternating current? The answer is sinusoidal waveform. What do I call it?
Sinusoidal waveform.
A sinusoidal waveform is a waveform that moves like a wave. It's repetitive. You move in between amplitudes repeatedly. Okay. We're now going to AC circuit containing a single element. This is the symbol for an AC source power. That's the symbol of an AC source power. And that's why the symbol is like this. It's showing you, bro, I'm going to reverse. I do reversal motion. I get what I'm saying? Good. Are we together? So, we are looking at AC circuits containing single element. Who is the single element we are dealing with here first? Resistor. Hello? Follow, we will solve questions together.
Yes, sir. Yes, sir.
We have AC power source. We now have resistor. AC power source and resistor. So the first element we are bringing into it is the resistor. So we have our current produced from the AC source and we have our resistors. The other elements that we eventually bring in are capacitors and what? Inductors. Capacitors and inductors.
Sorry.
Yes. Yes.
So you said an AC circuit can contain either resistors, capacitor, inductors. And it contains the three as in
Yes. We are going to get there in this class. Alright. the output voltage and current for this arrangement, hear me well, for this arrangement, VR equals to what? Now, what do you have here now? I. This I here stands for current. Because where did they get it from? From the fact that we know that when somebody writes VR like this, we're talking about voltage as a function of what? Resistance. So you try to tell that I know that this voltage is equal to what? IR. I get what I'm saying?
Yes.
Good. So we have that. So earlier voltage R was equal to V naught sine 2 pi ft. So automatically, given that V is equal to IR, we can bring in IR into the system. What would that be giving us? IR is equal to what? V naught sine 2 pi ft. Divide both sides by what? R. So our I is equal to what? V naught over R sine 2 pi ft. I see that? So voltage and current and phase. Now, there's something I'm trying to bring out here. When you did that subject formula for him, you could see that V, that is peak voltage over R is equal to this and and we also know that this current on its own is equal to what? Peak current sine 2 pi ft. True or false? That's it. So you can see. You can see. Alright. So from here now, we are trying to show that they are in phase. That the VM and the IM, that the volt at any point and current at any point are in phase. This one is maximum, which is like the amplitude. But at any point, they are in phase. How do you know they intersect at these regions? Okay, next. Now, we want to see capacitor in an AC circuit. We've seen resistance in an AC circuit, right?
Yes, sir.
Now we're looking at capacitor in an AC circuit. How many of us remember the formula for capacitor? You know that Q is equal to CV. So C is equal to Q. Baby. So that means there is a way we can relate V, right? So that we can write it in terms of Q and C. How would that be? V is equal to Q by what? C. So look at the output voltage for this arrangement is this. That is what we need to set our voltage to allow for a capacitor is to set it in this format. Recall, I'm starting again, V equals to V naught sine 2 pi ft. Watch. From here we can see that V is equal to what? Q by C. You can bring it in. Tell ourselves that this V in relation to capacitor can be equal to Q by C, which is equal to V naught sine 2 pi ft. Where Q is the charge accumulated on the main capacitor. Remember that capacitors accumulate charge. Capacitors are made of 2 parallel plates that stores charge. I get me now, and will prevent the exchange of that charge across the two plates due to presence of something we call a dielectric. So you have to be here to watch those values. So from here now, if I cross multiply, what does it give me? If I cross multiply, what does it give me? Q will now be equal to what? C V naught. V naught means peak velocity and peak voltage. Do you get that? Do you get that?
Yes, sir.
Alright. Now, to do better good, or to even do much better, this Q that is here, hope you know that this Q that is here is still equal to IT. True of us. Q is equal to IT. That means I can write expression in terms of I. Q over T, which I can call the Q over the T. True of us. True of us. Let's substitute this Q as IT in this place. So I say that IT is equal to C V naught sine 2 by F T.
Yes, sir.
And then you know that this I, you know that this thing here that we wrote down here, if there's a way we can still express it. There are ways that we could express it. How can we express it? By dividing Musa by what? T. So current is equal to, should be that CV is Q. Should be CV is Q.
Yes.
So then I say Q by what? Equals to, sorry, Q by T sine 2 pi FT. Some people don't like writing like this. They write in terms of dq over dt sine 2 pi ft. Okay, from here now we have CW V cos this. So what happened from here to here? Listen up. What happened from here to here was differentiation. Was what? Differentiation. So if I differentiate what I have here, what do they give me? And remember, I'm differentiating in respect to what? In respect to what? I'm differentiating in respect to t. In respect to t. So what does that give us? That gives us G equals to C CV naught sine angular velocity. So to differentiate this kind of thing is to just differentiate angular velocity and multiply the answer. If I differentiate angular velocity, I get only angular velocity. Multiply, what does that give you? That's how we got to this. Yes, it becomes cos. Yes, when you differentiate a sine function, it becomes cos. You can see that? So that's happening there. It's happening there. Now, this cos something. If you want to express it in terms of sine, you can. If you want to express it in terms of sine, You can, all religions become, you just have, what is it, form of Q. So I'll just have Q equals to C W V naught. This time around, I'm going to differentiate trigonometric identity. Sine velocity plus this one too. That's the same plus 90. You don't understand?
No, I don't understand.
There are rules in trigonometry. One of them is this. If I have sine theta and I want to change sine theta to something cos, it can become cos 90 minus theta. So cos 90 minus theta is the same thing as sine theta. So that's the same way how if I just had only cos theta, I don't know. If I want to change to sine theta, this one was 90 minus. This one is sine theta plus 90. So that's what we did here. This is like plus 90, but we just expect it in pi. So that's it. Hold on. Now, we have written this. We are at this point here. And that's the point I need. Is it? Yes, we are at this point. I'm actually being here. From up there, we got here. So, we have I equals to C angular velocity V naught sine angular velocity T plus pi over 2.
So sorry, please come back. I don't know what you did there.
I just brought this one out.
Okay.
Now, it's something I've already gotten before from here. I get it. So, I just brought it from there. And by comparison, watch. But from here, we're saying that I is equal to what? This, Abi.
Yes.
And we also know that our normal I is equal to I naught sine all these things here. What does that tell us? What does that tell us? From all, you said it earlier, both of these people can be expressed in this format. Both of them can be expressed in this format. Timekeeper, can I take a break to use myself? Sorry, I'll be back shortly. I just want to ease myself. Yeah. Thank you, I'm back. All right, so to continue. So, all right. So we can compare this expression here and this expression here. When we do that comparison, what do we have? We are able to establish something very interesting. How was that? This. Because since this is I and this is I, sign, everything will be the same. It means that these two things here are also equivalent. Do you know what I'm saying? It means that they are also very much equivalent. Okay, thank you. They are also very much equivalent. So I have I naught equals to C W V naught. Are we there now? I naught equals to C W V naught. So from here, you can obtain that V naught over I naught is equal to 1 over C angular velocity. This is a very important relationship. Do you know why? So I put that as C velocity, so I put that as angular velocity C. That's something like this. V naught over I naught is equal to 1 over angular velocity C. That is, this thing I can see here, I believe this one rings the bell. True or false? What bell does it ring? I said true. V is equals to IR. So it's like saying R is equal to V over I, yes, which is equal to this. That is what I say. And that thing, we don't just call it resistance. We don't just call it what? Resistance. We call it reactance. We call it what? Reactance. We call it reactance. And we have different types of reactants. Are we together? Yes. We have different types of reactants. We have capacitive reactants. We have resistive reactants. So the one we just did now is one that we got from capacitor, yes, when we added capacitor to the circuit. That is why we call it capacitive reactants. Reactants are represented as X. As what? X. But the subscript of the X is depending on the type of reactants. You are not following me on your own. So if I want to write capacitive reactants, how will I write it? X subscript C. That means X subscript C is equal to 1 all over angular velocity C. You see how we derive those things? It all began from here. When we change V to a C can come in, because multiply C got itself here, the moment C got there, so it's already a victory. It was already a victory. So look at them. What did we have to do to bring angular velocity into the CV? Into the CV. What did I have to do to bring angular velocity into CV? All I needed to do was to do what? Was to differentiate. Remember, going differentiate and let's move there. So which other way can we write our capacitive reactance? Recall, angular velocity is 2 pi f. Troubles. So that means this thing here can still be written like this. 2 pi f what? Are we together now? So, from here, we've gotten to there. So we can move. So I think I've shown you how I got to all this. Right? I've shown you this. So the quantity is known as the capacitive reactance. Measured in what? Ohm. I don't even know why it is ohm. For me, I told you that this thing here is actually gotten from here. It's actually resistance. So that's why it asks you what unit is capacity. It is ohms. Ohms. So you can see this equation here. You can see this equation here. Those are the things that help us to bring solve that issue. So this equation they show that the current in the circuit leads the voltage across the capacitor by pi over 2. Some of you did not catch what I just said. See this equation. And look at this equation. I see. You know, we have those two equations here. But this equation helps us to prove something. That the current in an AC circuit, it does what? It leads the voltage across the capacitor by what? Well, as you can see, in this page just pi t, but in this page pi t plus pi over 2. Do you see that? Unity. So physically, this is that current reaches its peak. It reaches its peak a quarter of a cycle before the voltage. Alright. So this is current. This is current. This is voltage. Current, and voltage, and current. As you can see this marking. Shows that current already leads by half, by a quarter. It's not about half, by a quarter. So it's an OBJ possible question. On this one. Okay. It's an OBJ kind of question. So we're expecting to see it. We're expected to see it. Alright. So next slide. We have looked at capacitor in an AC circuit. Now we are looking at inductor in an AC circuit. We looked at capacitor in an AC circuit. Now we're looking at inductor in an AC circuit. Okay, as the current flows through the inductor, along with capacitor, as the current flows through, this is the symbol of the inductor. So as the current flows through the inductor, there is an induced EMF in the inductor to oppose the change of flux through it. Are we together here? Let me wipe off this. So good. As the current flows through the inductor, and when the current gets it, there's an induced EMF. You know, that's the work by inductor. Capacitors first charge. And that's why when we derived capacitors, we brought in charge. But inductor induces EMF. Right? So as the current flows through the inductor, there's an induced EMF in the inductor to oppose the change of flux through it. All these things we discussed during magnetic induction. The EMF of the source must be equal to the induced EMF. The EMF of the source, the electromotive force of the source must be equal to the induced EMF. So now I'm trying to say. This is our normal expression. This is our normal expression for self-inductance. And the rule in self-inductance is what? A change in flux causes an induced EMF that produces current. And that current flows or acts in such a way that it goes to oppose the present activities of the flux. So, in this case, I have this, and it's equal to voltage. And while I'm writing V, I'm talking about voltage induced. This thing holds true in the lecture we just concluded, because we knew that the electromotive force was equal to what? L di over the T. So I brought it back here again, brother. Equals to V naught sine theta. The I is equals to V naught over L sine this. We'll talk about what that is. Please, let us look at this place. Let us look at this place. If we have this relationship, I will make, and I want to make my GI the solid formula. What will I do? What you can do? This is it. Call the expression for me. I have L di dt equals to V, which is equals to V
naught sine WT.
First thing first I want to do, I want to remove dt. And by doing that, what I'll be having is this. Cos multiply. But let me know what was multiplying it. Integrating will work, but that will bring my eye to normal eye. If it does not disturb me to go, there's a time I want to integrate because there's no time to do it. Look at this. Look at this. We're working with this one. We're working with this side here. I want to have just I alone, or the I no more. So I want to have the I is equals to V dt, V dt over L. Do you see that now? V dt over L.
Yes, sir.
And this whole thing is going to still be equal to
V naught sine dt.
true of us. Still going to be equal to that. Still going to be equal to that. Come on. We're going to play it very well. Now, how do we arrive at this? It's just a matter of us doing what? Just a matter of us if I say I want to come, let me take another approach. Let me use another approach instead. From here, do you know you can cross multiply from here? I can compare this equation. Since we said V is equal to this, I can just substitute this as V.
Okay.
So that my equation will just be what? L di over dt equals to what?
V naught sine angular velocity.
UG. So I can now even divide both sides by self-inductance. Dividing both sides by self-inductance gives us what?
If you use the I over dt is equal to V
Sine WT over what? L. We're almost there. We're almost there. Now we want to differentiate. We want to keep this thing, especially in such a way that I can differentiate this stuff in respect to what? T. And I can differentiate this in respect to T. What do we now have? What to cross multiply? What do we have? Gi is equal to what? V naught sine angular velocity dt over L. Good. You get?
Yes.
So what do we now have now? We have gotten an expression for Gi to be equal to all this. This dt here now is going to make it possible for us to initiate a differentiation. Sorry, I said an integration, right? That will help us to turn this thing from Gi towards I. So that's it. Okay. So what do I have? If we integrate that, now what will it become? I'm going to be integrating the double integration here. If I integrate the I, I'll get I. Because I'm bringing all these possibilities of i's together. If I want to integrate this one now, these ones, I can leave them out. I'm left with two. So what does that do?
So if you integrate sine w,
If you want to integrate this trigonometric function, remember it will not, if you differentiate sine, it gives you what?
give you cos.
Cos. When the differentiate cos, it gives you what?
Negative sine.
But if you integrate sine,
It gives you negative cos.
negative cos. And that's what we want to do here. That's what was happening in this place.
Second line.
This place here. When I integrate this, it turned into what? It turned into cos. I can see the minus there. right? Good. So how do we go about this? So our I is not equal to what? Integrate is only here to affect. Let us write minus cos first, angular velocity. Then eventually, when I differentiate angular velocity, once I differentiate angular velocity, what will it give us? It will give me only angular velocity. But instead of multiplying individual differentiation or multiplying, now that it's going to be division. And one of our angular velocity. So what do I have now? So I'm having I is equal to what? V naught over L W. Let me put a minus here. I mean, cos angular velocity T. You see it? Very, very easy. Very, very easy. So what do we want to do next? We've got to put once. What we needed was, we needed to find a way to bring inductance into the expression. That was what we needed to do. Now that we are able to achieve that, we know that this cos that we are having here, if we want to change it back to sine, what do we do? No, without differentiating now. Geometric functions. I'll just say I is now equal to minus V naught over L W. So this will now become sine. So let us write this. Become sine. Open bracket. So it was cos that was here. Yes. But turning from cos to sine, it will now be that thing that was there plus 90. If you are turning from cos theta to sine, you will press sine theta plus 90. Plus 90 positivity quadrant is just 90 degrees away from cos is 90 degrees away from sine. So I will have angular velocity T plus 90. What is 90 I have 90 as well? Pi over 2. Do you get it? Do you get it?
Yes, sir.
Yeah. So, how does this writing affect what we have?
What part of what? Minus?
Yes. You want to remove this minus. What effect will it have? Hold on. It's supposed to be minus here. Because I'm going from cos to sine minus. So, what do we have here? It means that earlier on, we came to the conclusion earlier on that current leads voltage by 90. I get it now. But this one lags by 90. Very good. Okay. So from there, what can we conclude? What can we deduce? Let's do a comparison again. Watch. By comparing again. What am I comparing with? See something? I equals to minus 40, so minus V naught, velocity, sine 2. Look at this. We want to do a comparison quickly. We want to do a comparison. Yeah? To the normal standard equation. The normal equation of I is equal to I naught. You get I is equal to I naught sine angular velocity T. That's what we compare. That's what happened here. That's what happened here. In this place here. No, there's no minus there. It's just straight up. So, watch. There's something, when earlier when we wrote this constant said something like this, if you check the quadrant, all is positive here, then it is, they did it as T, C, A, S. Sine, cos. Sine is actually the one that leads cos by 90. That's right, cos leads sine by 90. So the correct expression was what we wrote before. Yes. When you were changing from cos to this. So this minus came to play here when we wanted to open. It took its effect inside there. So if I want to remove this minus, it will affect here. Do you understand? Trigonometric identity. That's what it will affect. So now I can do my comparison. Now the minus of the. So I can do the comparison. Right? So that comparison now is that what? Is that I is the one that is equal to what? V naught over L W. So I'm having I naught is equal to V naught over L W. Let's bring I naught and V naught to orient themselves in such a way to form a resistance expression. I don't know normally R is equal to what? V over I. So can we bring that here? Yes. What will it give us? 12 volts. The role of this is the resistance, 12 volts.
Yes, sir.
But what kind of resistance is this? We call it an inductance. Inductance resistance, but we don't call it resistance, we call it inductance reactance or inductive reactance, which is equal to what? LW. Reactance symbol is what? X. Then induction L. This thing here can also to 2 by F L. That's all we have here. Yes, they can give you the inductive reactance. I want to define the inductance itself. Yes. Okay. Next slide. So in this case, we know that this kind of inductance it lags by what? 90 degrees compared to the current. So the current in this one lags the voltage across the inductor by what? By 90, which is pi over 2. So we need to know that. So next. Alright. And ILRC sections. Do you know what we've been doing since as in one component element is executed. Where we did for where we had only R, we've done for where we had only C, we've done for where we had only what? L. Now, we are now looking at where we have what? L, R, C. And look at the loop rule is there to play the catch-up loop rule. A kick-off loop rule. Kick-off loop rule. Alright. So whenever you have a circuit that is enclosed, we know that the sum of potential difference there should be what? 0. And looking at the way this is enclosed, the current is usually going to be like what? Same constant. Do you get that? It's going to be like constant. Now, it means that if we do the voltage from this power source and we subtract Ri L minus L the I over the T minus Q over C. All these things I mentioned, I really know what they are. Those are the different forms in which we brought in the parameter as voltage. You know, every one of them came as voltage. Let's see if there's anyone I've not came to. See this one here. This was the IR. That's in here. This was the LD over GT. That's in here. You don't want to be writing the resistance over times. They are writing as voltage already. So everything here is voltage. Voltage of the alternating power source, voltage in the resistance, voltage from the inductance, voltage from the capacitance. And we're saying that all of them should be equal to what? 0. Do you get that? Do you get it?
Yes, sir.
All right. Next slide. So the IRL series circuit solved using kickoff rule. Now, there are many things that we're going to arrive at while trying to derive this. We have our normal voltage function. In the normal way, that was ordinary V, but that ordinary V is actually V naught sine this. Then we have this. We have this is the resistance, the inductance, for the capacitance. So, eventually, when you plug it into a DE, you have all this like this. But that's not what we're interested in. What we're actually interested in is press next. Press next, all these ones are just derivations. One of the things that we're interested in is what we see here, not even this one. Still go for that. When it will sum up to. Yes, that's why I said this part of this. So here, we have tan theta equals to all of this, after all those derivation, it all landed in the fact that tan theta is equal to this. Now, let me just bring that side out. XL minus XC over R. This is finally how they act in reference to Normally, the general what they call action is with the impedance. That's why eventually this is going to be like our x, this one is going to be like our what? Y. So if we want to retranslate it into the vector form, I'm saying that our in general resistance, summative resistance will be square root of what? XL minus XC squared plus R squared. You get it? So it exists this way.
So this formula now is equal to impedance.
Yes. This one is equal to Z. Yes. So next slide, the summary will be good. Put that very soon. Okay, so you can see it here. See how long it will come to this conclusion. So this is one of the most important things you don't want to forget. Z, which is impedance. So if you want to define impedance, what will you call it? If you want to define impedance, how will you call it? What will you call it? It's like the resonant reactance in the AC circuit. Because every single thing inside this AC is actually still a reactance. All of them are ohms. So it's like the resultant of all reactants in the world. In this circuit. So that's it. That's it. End of writing, just take note of it. But we should know that our XL most times is usually greater than what? X. Next. Okay? So we know where this comes from actually. It's not that for that. Next.
So the previous slide.
Previous. So,
I got because the like
because this thing here is like the summative resistance.
that replaces the R.
Yes. So it is now being like the overall R. Phasor diagrams. So we are having the voltages across the components are out of phase as shown in the phasor diagram. They need to be added as vectors to get the total voltage. Okay? Next. All the things I just described in phasor diagrams. Consider this VL minus VC. So the voltage over the capacitor, the voltage over the inductor. You can see how they represent themselves. We have two vectors here and one in a different direction. So this is another mechanism graphical method to view this. But nevertheless, this is like the overall effect of your voltage. So voltage is equals to the overall resistance, which is saying Z. This is Z, right?
Yes.
Z what? I naught. So it's still the same thing if you write it opened like this. Yes. Power in an AC circuit. Let's look at power in an AC circuit. circuit. So, normally power is equal to what? IV. So you know that power is equal to IV. Right? Right?
Yes, sir.
So, most at times, the whole of this thing here is for them to come to the conclusion that power is usually RMS B RMS. Yes. That's what it's driving at. So, you get it?
Yes, sir.
That's what they're driving at. That's the power average. So the consistent is just the action, the direction of action to reach the act. Next slide. So here now, we have other ways to represent power. Power can also be equal to what? I squared R. You get it? But if you have big power, you can't give it time because that one's for energy. You can't give it time because it's for energy. It's for energy. Okay? And then do that. Okay, next. Example 1.
What of power factor?
And then
How do you find the power factor and phase now?
that's visible in this thing now. Fine.
What of the power factor?
That's the body components. The first expression I showed you, when we did this one, I put this here. That's the factor there. You can still open it if you have to open it. Alright. So, next. Okay, look at it. Go back to the previous. See, they showed it here. You understand? So I told you it's just what is here. And let's go. Okay? So, what's important next is this resonance. Condition for resonance. I don't know. So under what condition does resonance occur? Under what condition? Listen up. Now, resonance in an RLC system. Under what parameter exactly affects resonance? Affects resonance. What parameter affects resonance? Between resistance or reactance, current, voltage, which one of them affects resonance? You know that we have resonance in AC circuits. The question there now is that among all the parameters, yes, in the RLC circuit, which one of them contributes to resonance the most? Resonance, why? Very good. So that's the major thing. So out of all the reactants, it is the inductive reactants and the what and the capacitive reactants that controls the resonance of an RLC system. What must happen to them? They must be equal. They must be equal. You know I told you that the XL is usually greater than the XC.
Yes.
You understand? But the moment the XC has been able to increase to equate with the XL, it will initiate that resonance. So, if you want to check it, This is what you'll be having. So let me read it. So look at it. All this one they are speaking is grammar. XL must be equal to XC for resonance in RLC circuit to occur. What's the formula for R for XL? 2 by F. Formula for XC. 1 over 2 by FC. Right? Yes. So it's as good as saying angular velocity L is equal to 1 over angular velocity what? C. Let's cross multiply. What do we have? Angular velocity square LC is equal to what? 1. Abi? So what do we now have there? It's equal to what? So take this square. Angular velocity is equal to what? 1 over square root LC. So this is it. So if they ask you for the frequency of resonation, you can as well just bring out to what? 2 pi ft and work with it. You've gotten your. Which is that? Okay, yes. No. So they tell you to calculate the frequency. They tell you to calculate the frequency at resonance. How do you do that? 2 pi f. I think that will give you what? That will give you f equals to 1 over 2 pi square root LC.
What happens with T?
T is not inside this. So you have 2 pi f is equal to 1 over square root. If I represent by 2 pi f will be equal to 1 over 2 pi square root LC. Sharp. That's it. All right. So, next slide. We'll now describe resonance. This slide will derive already. Continue. Just keep going. Just go down. Let's treat that. So I'm looking at RLC parallel circuits. It's nothing much of a problem. The normal rules applies about junctions and all. Normal rule applies about junctions. So there's something we define as an admittance, which we call Y, and an admittance is the reciprocal of an impedance. An admittance is the reciprocal of an impedance. And the unit of admittance is called Siemens. Siemens, which has the symbol S. Admittance is the measure of how well an AC circuit will admit or allow current to flow in it. A very likely potential Joupert theory question. To define admittance.
So, see, what you're saying is that impedance is the resistance.
Yes, impedance is impeding current flow. Admittance is supporting.
So what allows current to pass?
Yes, it is the compliance factor. That's the compliance factor in AC circuit. So, admittance, the total admittance of a circuit is the sum of the parallel what? Admittance. The total impedance Z of the circuit is therefore what? 1/. So that's it. As the case might be. That is it. There's another one we call susceptance.
What does that mean?
That one is the reciprocal of reactance. That's the susceptibility to a particular reactance. Don't forget these things, though. Because of your OBJ. Usually you don't be losing some kinds of small marks.
What do you call the last one?
Susceptance. Susceptance. It's the what? Reciprocal of what? Reciprocal of reactance. So we have, next slide. So we have the capacitive susceptance. We have the inductive susceptance. You get that? So please take note of that one. Next. That's the last slide. So, I think that's where the work ends. Yes, that's from here. So, we are going to be running a question and answer session right now. Are we together?
Yes, sir.
So before then, I want to take a 1 minute break. Okay, let's see after 5 minutes. Okay, so let's just start. Let's just start. An AC source has a peak voltage of 339 volts and supplies a resistor of 50 ohms. Determine the RMS voltage and the RMS current. Sometimes I just realize I'm going to myself and I hasn't put it there. So let's solve it. Yes. What's the value of the RMS voltage?
The answer is 239.7 volts.
Nice one.
And then RMS current
What's the value of RMS current?
35.35
Go on. Check what you did. No. That's 50 ohms. To get your RMS current, you have to get it from, because they don't give you the peak. You have to get it from the RMS voltage. So you have to get it from the RMS voltage. Have you seen it? So you've just learned how not to do it. Yes, every mistake you make, you have learned one way not to go about a problem. So in the exam, don't use that value. Number next. Okay, can I read the next one? A 0.40 H inductor Zero bonds. Okay, that's my one. What do you get? Yes. Can I read this one now?
Yeah.
A 0.40 H inductor is connected to a 50 hertz supply. What's the meaning of H? Do you see how my name used to spread in physics?
Yes.
Tired. My name. I'm telling you. Don't worry. A 0.40H inductor is connected to a 50 hertz supply. Find its inductive reactance. You just need to remember that FL is equal to what? That's all.
135.67.
Please give me 1 minute. a point in time where we solve problems. So we keep solving problems and we keep defeating these problems. Let's go. Question, what are we? So this one is from the series RLC circuit. A resistor of 40 ohms. A resistor of 40 ohms. And then,
Yes, sir.
another point. A resistor of 40 ohms, comma, an inductor of 0.20 Henry, that's my name, and a capacitor of 100 microfarad are connected in series to a 50 hertz, 240 volt supply. Find A, inductive reactance, B, capacitive reactance, C, the impedance, and D, current. Now, in every exam that has to do with AC circuits, please do not approach any question without presenting a circuit diagram. That's a disrespect to the field. It's an imaginative field, and we need diagrammatic presentation. So, all three things are there. Are you done? Let me see your diagram draw. We know that they are all in series, and they connect to the alternative current source. The Department of Physics in every university are well as disciplined people. What's the frequency I told you? Okay, so obviously this is a Nigerian-based question now. Because if you're USA, what frequency of the AC circuit will be expecting? 60. So here we are having what? We are having 50 hertz, you put the voltage. What the AC voltage there? 240 volts. This is where you used to write just below the what they call it, just below the alternating current sign. So on this end here, we have our resistor. Yeah.
The battery and the cell sign of why is the voltage at the bottom?
The what?
The cell sign that we put.
This is not cell.
What's that?
This capacitor symbol.
2 parallel lines.
What do you call the capacitor symbol?
Carriers.
What is it called the capacitor?
Carriers.
This is the difference between cell and capacitor. Both of them have two lines, but it was a cell. One line is longer than the other one.
Okay.
When they are equal, that is a capacitor. It's mimicking the physical presentation of the capacitor. That's parallel plate capacitor. You have two parallel sides filled up with a dielectric.
Okay.
So that dielectric now is just leave it opened in the presentation. So we have 40 ohms. We have 0.20 Henry as the inductance for the inductor. And capacitor they will have
100 microfarad.
100 microfarad. I bet you know I'm going to operate in that. We won't operate in microfarad. So we operate a farad. That micro is not a unit, it's an order of presentation.
So we need 10
-6, yes. So find the inductive reactance. What's the formula for the inductive reactance?
Pi L is equals to 2 pi FL.
Thank you very much. So inductive reactance XL is giving us 2 pi FL, right?
Yes.
So please put in parameters and let's get this done. XL equals to 2 times 3.142 times 50 hertz.
Pi L is equals to 62.84.
62 point what?
84 m.
No. And a reactance, there is usual thing. Thank you very much. Measure in ohms.
Oh.
People make that error because they hear the word inductive reactance. They think that to take the unit of the inductor. It takes the unit is the resistance.
Oh.
So we'll go for the next one again. Capacitive reactance. Capacitive reactance. What do you have on that one?
Pi C is equals to
Yes.
1/2 pi FC.
Okay. So you are saying XC is equals to 1/2 pi FC, right? So what does that give you?
You
Capacitor is 100 times 10 to the power minus 6.
1.6. So you have 31.83.
31.83 watts.
Oh.
Thank you. All right. The guy at the back, give it us. You are on point, right? So, what's the next one? Impedance.
Yes.
So, the impedance is like the what?
It's like the resulting.
Thank you. The resultant of all reactants. Good. The resultant of all reactants. So, what do you have on that one?
Then is equals to square root of pi L minus pi C all squared plus R squared.
Okay. So, I'm having Z is equal to the square root of, yes, square root of what again?
Pi L minus pi C all squared.
Okay. So, what does that give you?
Pi C all squared. All squared. Squared.
So, what does that give you? Then that would be 40 square as 1,600.
That gives us 31.01.
So our impedance is 31.01 watts ohm. Then the last part of that question, right?
Find the current.
Current. So when I say the current, we know that it's a series setting, it's a series setting. So obviously, the current at one point, there's no point in time when the current is going to change or anything. It's the same current flowing through the circuit, right? Closed circuit. So what am I going to use to get the current? I'll use the resultant reactance. That's the impedance as resistance. Do you get it? So I'm saying that V is equals to what?
IZ.
IZ. So I is equals to V over Z. Value.
I is equals to.
Yes. Yes.
I is equals to 7.73.
I is equals to what?
7.73 amperes.
What did you press?
240 divided by
Alright.
31.01.
Okay. So that's it. Kindly reconfirm this value. Reconfirm this value. Because the resultant value is supposed to be greater than the component value. To confirm this.
Okay.
Because we have one component already, but the resultant is very good. What is that is what? Am I correct? Check. 62.84. Is that it?
Correct, bro.
It's correct.
If your question is wrong.
It's not my question. When you are having resultants like this, and first value result, R was what? R was what?
Oh.
You didn't include this. Because I'm like, if you are doing resultants, your resultant can never be less than. It's just like it's going to be the longest.
Yes, sir.
So when you are working, try to work with precision as well. You should have a preconceived value. Think of it.
Think of it, do this, sir.
Oh, yeah, quick. What's the value, please?
The value is 50.61.
Now I'm talking. 50.
61.
61 ohms. Okay, now it makes sense.
So your current is 4.74.
The current, David?
Yes.
4.74
ampere.
ampere. Thank you very much. Let's move.
Next question, sir.
Determine the power factor. Okay, in question 4, in that question 4,
Okay.
they want us to determine the power factor. And when we determine it, let us check. Using that power factor, let's check if it's a lagging or a leading factor.
So, what angle? Why is it +9?
If XL is greater than XC, it means that it's the lagging power factor.
Why is it +5?
We just need that cos that.
+5.
Yes, that cos phi. And we know it is still equivalent to Z all over R. I mean, no, R all over Z because Z is the bigger one. R over Z. What does it give you? Now my XL, since XL was 62 XC, so XL is greater than XC.
+5 gives you
0.791. Check.
You're not looking for the angle, you're looking for the
But I've gotten the angle now.
It's because inverse of R over Z.
Yes. What does it give you?
Give you 0.9999999.
That's 40 over 50.6. Then cos inverse. Marachi, have you had dinner? Have you had? I feel you should go and eat too.
I made mistakes, sir.
What's the value?
The angle is 37.78.
Okay. It is the cos inverse I want to. Okay, wait. That it was 0. It was when you divided, it was 0.
Yes, just
Okay, good. So the power factor is that value lagging. Look at that's how you present it. You say when they ask you for power factor, when you've gotten that That's the you don't get the cos inverse. That value in front. You state it there. You forward check. Is XL greater than XC? If XL is greater than XC, then it is lagging. By what factor is it lagging? By that factor you got. 0.7. Yes. So we are saying it is 0.791 lagging. How about if this one, if the SC was greater than the XL? Leading. When if they are equal, that's it. Good. Resonance. Let's go for the next one. So in all our quantification, we are going to be utilizing power factor inside. So for example now, they say using the same question 4, determine the average power consumed. Yes, cos phi, which we know what it is. I didn't hear you. 898.7. Good. Good. Watts. So let's move.
Next question.
Yeah. A series circuit has inductance 0.5 Henry, and capacitance 25 microfarad. Find the resonance frequency. Find the resonance frequency.
Resonance frequency is 45.01 hertz.
Yes.
At 5.01.
Yes. Yes. But did you get it? You're still working on it. But you know what to do. You know what to do, right? Yeah, let's work on getting an admittance.
Your impedance.
Yes. The circuit has an impedance. That's a boring question. Leave it. Leave it. Now let's work on this. A resistor of 100 ohms is connected in parallel. A resistor of 100 ohms is connected in parallel with a capacitor having a reactance of 200 ohms. Okay, let me come again. The resistor of 100 ohms is connected in parallel with a capacitor having a reactance of 200 ohms. Reactance connected in parallel with the capacitor having a reactance of, do you understand? Having a reactance of 200 homes. Find Jesus. Find A, the conductance. A, the conductance. B, the capacitance. Sorry. B, the capacitive susceptance. And C, total admittance.
Yes.
So what's going to be our value? I look for conductance, capacitive, susceptance, then thank you. Total admittance. Loss of resistance. That's the
So your conductance is 0.01.
yeah. Unit. Semis.
Your active susceptance is 0.005.
Yeah.
What's calculate the total impedance? Calculate total admittance, use it.
Don't. Use it. Depends it. Even if how many circuits, how many elements are here?
The resistor and the reactor.
You work with these ones. I think you won't tell me so you don't forget everything again. I know you come back. Have you done it? Zero point. They even ask you, I can't see where they ask for it. They don't ask for impedance. They ask for impedance. You can do it direct. You get the admittance for the ones available one by one. Then get the resultant admittance. For example, conductance is an admittance, it's the inverse of resistance. No, I have gotten everything now do. So that is on square root modulus. I think there are only two that we have. Oh, wait. That one that you got. What do you get for? When you divide it, it's supposed to be the thing now because it's inverse. 1 over it. To me, you've got impedance. Eh? What do you say I've got impedance for? 1 over that is what? Be solving. Solve the normal one I told you. Start solving. Start solving the way I told you. This is what I'm going to do. Yeah. What's the value of the conductance?
Conductance is 0.01. Yes.
0.0 what?
0.01.
0.01. So that's our first susceptance.
Then the susceptance is 0.005.
0.005 squared. Is that all I have?
Yes.
Okay. So, punch it in the calculator for me.
To give you 0.0111.
0.01. Everything together?
Yes.
Okay. 0.0111. So that's it. And what's the unit? Capital letter?
Yes.
S.
Next question.
Okay. A series RLC circuit. A series RLC circuit is connected to a 240 volt 60 hertz AC source. The components are connected to a 240 volt, 60 hertz AC source.
This is the US.
Yes, it's a US based current power for. The components are resistance R equals to 30 ohms. Inductance N equals to 0.5 Henry. 30 ohms.
N is equal
N is equal to 0.15 H.
1.5 Henry.
S is 80 microfarad.
So,
Let me ask you if it's not time for rotation. It's not time for rotation. No, not to solve because it's part of the rules. It's not time. I mean, what's the last thing you wrote?
T is equal to 80 microfarad.
Does that mean? I. Let's drop it in. I'll still need the video. Does that mean inductive reactance, capacitive reactance, impedance, circuit current, phase angle, power factor, and bridge power? Inductive reactance, capacitive reactance, impedance, circuit current, phase angle, power factor, average power.
Your KL is equals to 50.54
Mm-hmm.
ohms.
Next one.
Your can C is equals to 39.78 ohm.
What option is that one?
Your can C. Alright.
Okay. What do you get? What do you got?
39.78.
Yeah. You did not do the one all over. Yes.
Z is equals to 34.67.
I didn't get that.
Z is equals to 34.67.
No.
Yes.
No. No. I'm gonna go for it.
It's 8.05.
Thank you. Thank you. What did you do before? Chief, are you good? Are you good?
Where is the 6.33?
Hold on. Yes.
Phase angle is 30.1.
Chief,
Phase angle is 30.
I heard you.
No, no,
It's correct.
30.1 degree.
Hold on.
Yes, 30.09.
Which one again?
As tan inverse of chi L. Chi L minus chi C over R.
You are doing this intentionally. What do you get?
I told you, say you didn't.
No, yes, sorry.
That's that inverse of minus Q.
Why do you give that name? Which one is Kael Kaisi? Next. Yes.
It's 7.96.
Yeah. So is it lagging or leading or resonance?
XL.
Okay.
So your power factor is 0.99 lakh. What does it?
0.999 lagging. You know the funniest thing? AC circuit is the cheapest part of physics. Do you agree with me?
No, sir.
Chief, you agree with me? Yes, it's the cheapest part of physics. You don't think so? Which part of physics do you think is the best? It's easier. What part of physics do you think is the easiest? Yes. I don't feel that one is easier. Shit, sad, man.
So your average bar is 1,512 watts.
1,000.
12 watts.
Let's try one more question. Let's try one more question. Now we're going to topic 29. Topic 29 is done. I thought it's short one. We'll need it. And let's go. I just want to finish these topics. It's not just about completing the hours. It's about finishing the topic. We still have to go and solve 50 questions. You don't. Okay, I don't think that. Admittance of 0.025 S, that's same as find its impedance.
Impedance is equal to 50 ohm.
Yes.
What is the value of impedance?
Which one is 50 ohms? Check what you're saying, bro. Check what you're saying. 0.025.
Just 40.
Okay.
40 ohms.
Okay. Yeah. Listen. Is it atomic physics or atomic structure? How did I write it? Atomic structure. No one ever is the best. Anyway. What's that like this one? So, then, is that was, right. So, we are now in module 30. I think it's better if we start this like the third rotation, the next rotation. So the last one's for the night. That week. Okay. I think so. I think so. And I just did. How many hours before the? How many hours before the next rotation? Something on the gentle. This one. Why? There's nothing inside this one again. I'm going to solve on that one. Okay, so computing. We are getting talk. Same thing.